Hello guys, thanks for coming to Olewave channel. We're a channel that's focusing on reading the latest archived works on speech and NLP research work. Today, we're going to be continuing reading the famous work Clip by OpenAI, and the title is Learning Transferable Visual Models from Natural Language Supervision. And since we have finished the introduction, the algorithm, or the approach part, and also we finished the experimental section, today we're gonna be finishing the rest part of the paper, which include the miscellaneous sections and also the conclusion, the appendix. Okay. The section 4. For those of you who haven't seen the part 1 and part 2 of this paper, you can search clip CLIP on the YouTube channel. On my YouTube channel, it's called Olewave channel. So you will find the recordings. You can read it and then come to this one. Okay. Section 4. Comparison to human performance. I think the authors raised a important question, which is whether this clip pre-trained model compares to, how does it compare to human beings' performance? Well, I think one thing the authors did mention that was the motivations of the human evaluators when given the task, because the task would be zero shot, because they're talking about the zero shot performance. Talking about zero shot performance. And for example, they ask about the cat or dog breeds. I mean, for me, I'm no expert on this. For me, it would be the zero shot task. But I mean, I would really not be motivated if being asked this question. I would tend very much likely to say I don't know or just random guessing. But if there's a prize or a competition, I would be more motivated. So this is, you can see that in their settings, I don't think the humans are very motivated. But the results, you can say figure 15. Where can I find figure 15? Not figure 15, sorry, it's figure 16. Comes to the next page. They ranked the image categories. The x-axis is the categories of the images. Y-axis is the accuracy of each category. And you can see that if humans are given some sample to learn, in given one shot, right? Just tell me, suppose this is like a Labrador dog breed, and show me another one to me. That would be zero. That would be a one shot. I'm sorry, one shot. But if nobody tells me this is a Labrador breed, and I'm just showing the first time this breed, that will be zero shot. But clip is facing the zero shot all the time. Okay, and you can see that. How do you see that? And this is the, what do you call that? They draw a line over the dots, do the approximation, linear approximation, and you can see that it's zero shot clip is better than one shot human, being. But I guess it was because during the training of the clip, due to the special training framework of the clip, it must have seen some concept like the dog breed or cat breed. That's my guess, because I don't think the authors mentioned the data overlapping issue in the dog or cat breed one shot classification. Well, I think the general purpose of this section, the comparison to human performance, was just trying to say that the zero shot clip model is indeed better than one shot, not only zero shot but also one shot, a few shot human being performance. Okay. Section 5, data overlap analysis. Well, I think this is drawing more and more attention recently, because since you have been using the pre-trained method, you have crawled lots of data from internet. Whether data you got from internet has any overlap with your testing set or validation set. And this is reason why the authors they run the duplicate detector. How does it work? Remember what page is this? Okay, this is page 17. Quickly jump to the last appendix. They build a duplicator detector. I think it's appendix C. Yeah. Okay. They actually is fairly straightforward duplicate detector, or I would call that a vanilla duplicate detector. It's just use the nearest neighbors in the model learned embedding space. Okay, it's very simple. Okay, suppose you have the clip model pass a, I think pass an image into it, right? Does the clip need to? I don't think it's necessary for the clip to take a prompt. You know, you can send the prompt to be empty. Say you send an empty prompt. That's my guess. That might be wrong. Okay, it's an empty prompt plus a image. Okay, suppose you do image one, and you got clip, you got vector one. Okay, then you do the same thing, but to replace the image one with image two. Second, and you can get another vector, vector two. Then you compare these two vectors in the feature space, okay, or the model learned embedding space, to see whether they are close to each other, and to check whether if they're very close, there might be a duplicate. Okay, and in order to reduce the noise or something like to make the model or detector more robust, they are very smart to build a near duplicate detector, which leveraged synthetic data augmentation. How does it work? But I think this is not new in computer vision. Also, it's not very new to speech people like me. Basically, they would try to do something like a random cropping or zooming, or things like manipulate the original image number one, just augment into the variations of image number one. And in this way, they can receive lots of images which are similar to image one, but you would consider these as duplicates of image 1. They are not exactly the image number 1. And at the same time, they can also train a model to do this. So the augmentation be done in a model generation procedure or synthetic procedure, but also you can see that the model can either be trained, maximize the similarity, or minimize the similarity. So you have the positive samples and negative samples, right? And then so you can use the classical info NCE loss. Okay, that's very standard. You train this type of model, you generate lots of data, and then you use this data to help your duplicate detector to be more robust. Make sense? Model architecture wise is that these are some parameters like ResNet 50, GLU activation, things like this. These are trivial. Let's go back to page 17. After we finished understanding their duplicate detector, this is lots of pages. 17. Yeah. After they build a duplicate detector here, they just say, I can set the threshold, then categorize, classify the whole set into number one, overlap the data set or the clean data set. Overlap means duplications, okay? You can think about whether the overlap might be something like, okay, in this part of the training set, these images are fairly close to my testing set or validation set, okay? But clean is very different, not non-duplicates. Okay. I think it's let's jump to the figure to take a quick look. So now we come to figure 17. This is a statistical significance study on the overlapping issues. The first we can check the left figure. They're suggesting that what is the x-axis? It's called the detected data overlap. And the y-axis is the difference in accuracy on overlapping versus clean data. So the common sense tells us once you have overlapping, your classification results should be significantly better than on the overlapped data compared to the clean data. Make sense? But indeed, it's not. So most of the time, I would say the result is better or not worse. But there are certain data sets. Let me use another pen. Red. These. You saw this? Or also this. See? Those are they're saying that I think they're saying that only 5 data sets. That's the 5 arrows I made here. Or might be not correct on this. Oh, yeah. First of all, these 5 data sets, they're getting worse results on the overlapped data set, which is they talk about this because I think you can see they are saying that the reason of these, they attribute that to this one. The underlying data distribution may shift between the overlap and the clean subset. So what they suggested is probably they're suggesting that the overlaps are indeed not reflecting the true distribution of the model they learned from. So this explains that some overlap data set has a very significant accuracy job on the overlapped part. It's, yeah, remember the keyword distribution shift. But I cannot fully understand that, because does that mean once you have overlapped data over there, your model didn't learn the distribution of the overlapped data? So the eventual model got worse? Or say because their model is, think about their zero shot clip model, it's just one model. What that possibly means that for certain models like this, for example, KNET 700, the amount of the data in the training set is so small that, I mean, the distribution of the learned model doesn't reflect the KNET 700 data, even it has some overlap. That, I think I checked their paper. I don't think I got a straight answer. And that's one of the things I think this paper shows some problems on, because you can see that the paper talks a lot of aspects, but they do not or did not dig into these aspects. They only mentioned that aspects. But my take on this was the authors want to shed light on different aspects rather than provide an answer on different aspects. They would more likely to encourage the readers to explore these issues themselves. Okay, that's the point. And then they're saying that English is saying that only 5 data set. This means that they're confident that this exclude a 0% accuracy difference. That means the exclude 0%, that means that it's a affirmatively you got accuracy indifference. I think these are the 2 things mentioned here, I think. 5 things mentioned here, I think. Yeah. That means indeed these said, I think what they meant is that they have over 20% difference in zero shot accuracy, right? It's a huge difference. And that explains the distribution, or that reflect there might be a distribution shift. And also 2 of these data sets do worse on overlapping data. Yeah. What they're suggesting, these 2, see? ImageNet Sketch and the KNET 700. I hope that will clear some of your doubts, because I think this section is not easy to read. See, these 2, they got worse than the clean data on the overlapping data. Okay. And now let's see the right section, right part. Right part is that since the percentage of the detected overlapping, So this is still the detected data overlap. And this is the overall accuracy change due to overlapping. Okay. And let me just give you the conclusion. It's taking time to explain. They're just saying that only 6 data sets. That's the oh, let me read this, okay? The overall test accuracy gain due to overlap is much smaller, with the largest estimated increase being only 0.6% on bird snap. Yeah, you can see that the numbers, what they means is that according to their analysis, I think they showed it in the text, the portion of an overlap in the whole data set is not much. So this is the reason why if you compare the whole set versus the clean set, I mean, you see the due to overlap. If you just remove the overlap, the data set, the difference in performance is not that much. You can see this is a percentage, and the biggest number on the y-axis is 0.75. It's even less than 1%, so it's very trivial. So yeah, and what they're suggesting that is that only 6 datasets are the accuracy improvement statistically significant when calculating using a one-side binomial test. So what they're suggesting is probably I think what they're mentioning is these 6. You see, for those 6, all the p's are less than 0.05. That's the standard value of p, right? It's less than 0.05. So that means the improvement are significant. Clear? If you're not knowing what this is about, you can check some keywords like significant testing or testing. Just search this. You will find some tutorial on this. Okay. Yeah. I think the authors talk about the overlapping issue. What their conclusion is that even there's some overlap, the result does not change much regarding the accuracy. So, which was caused by the overlap. So you can safely assume that the model can be used for other domains, other tasks. You can just forget about the overlapping issues if you're working on some engineering problems. Limitations. Section 6. Limitations. Okay. Limitations. What are the limitations? Or the cons? Okay. I think one thing is that I think this is the biggest limitation of it. So you can you can see that the authors compare their performance on different data sets, but indeed the performance of the baseline is well below the overall state of the art. Well below. Yeah, the author they agree with on this. Which means that how do you say that? Because when they compare that with state of the art, they're comparing their zero shot learning with the supervised learning method. So, I mean, from common sense point of view, you get what you paid, because for their zero shot learning scheme, they did not spend a lot of effort on labeling the data of that specific domain. So it's very hard or unimaginable for them to supersede the supervisedly trained state-of-the-art model. Yeah, also there, if you just go back to section 3.1, I think I covered that in the previous experimental video. You check the second video of clip in the experimental section. I think it's very, very weak compared to on several kinds of tasks. Yeah, I mean for the MNIST task, then I can think about, okay, even you train with some vanilla VGG model, you can definitely get better than 88%, I think. But the zero shot clip is not doing well. And also, they're talking about the limitation. Remember the clip model? Let's remember what the page of this is. Let's go to the algorithm. Yeah, this one. Let's see the figure one on the right side. So you can see you perform image related classification or regression task. Besides a image, you have to provide a prompt, and the prompt you have to feed the n different you can either call categories or concepts. Yeah, the author mentioned these are concepts. So you can see that the zero shot inference or learning is fairly limited to those concepts, and those concepts have to be seen before in the training set. You see what I'm saying? If for example a word dog has not appeared in the training set, they couldn't do the zero shot learning stuff. For example, suppose they finished training the model in 2022, but there's a new brand coming out in 2023, or the concept came out in 2023, but the model has never seen that concept, and this is the limitation of the model, because the model wouldn't be able to understand the concept, or there's no way for you to feed in that concept because the text encoder won't be able to take in that concept. So any concept has to be seen in the training set. I hope that's clear to you. Well, you can also say, I can just try to use another text encoder to encode the concept. That's probably doable, but I think that's not what meant. There's just recommending. Suppose you have some unseen concepts. You definitely have. Their architecture or their framework wouldn't be able to handle this. That's what they meant, or that's the take-home message. Only those concepts. Okay. This page. Oh, that's also another thing, I think, for people who just started zero shot transfer learning. You want to read this. Think about zero shot transfer learning. You're not supposed to have a training set, or a training set has label or has labels inferred from a seed model. You're not supposed to be doing training. But you do need some data set. Let's say it's a validation set, so that you can make sure that your system's parameters are well tuned. So the authors are very frank. They're just mentioning that they're indeed not doing the pure zero shot or true zero shot scenario. So they do have full validation sets. And I don't think it's wrong to use them. For example, they perform on different tasks. Remember, they performed that on 50 or 20-ish data sets. Those data sets, they have validation sets. I mean, they can use them. So, but the question is that, or the issue is that these are not indeed true zero shot scenario, because the true zero shot scenario would require, or would have to, you have to eliminate this validation set. For example, your model has been trained on conversational speech, but today I suddenly ask you to recognize presentation. So this is, you don't have a validation set, because this is a practical use. You just are, you have to face the true zero shot scenario, and there would be no validation set for you to tune your parameters. Okay. They just started to mention that the biasing, because this is the limitation. Because where's my pen? Because they train these images, they crawl on internet, right? And these data are unfiltered and curated, and this may result in social biases. There's no human intervention to avoid or possibly avoid social biases. But they will cover that in section 7, which is the following section. Broader impacts. They're talking about, what do you call it, social bias here. Okay, for this section, I know this is very controversial, and I'm not trying to say this is wrong or right, or I'm not trying to share my personal opinion on this with you, but I'm just trying to discuss the content of the paper from a technical point of view. Okay. Broader impact. They have a wide range of capability due to its ability to carry out arbitrary image classification tasks. Yeah, they don't have to train. Zero shot. And they do mention that they show a great potential or promise. It's very promising for image retrieval or search task. If we can, yeah, let's quickly go to the appendix section. Let's see how they work on the image retrieval or search task. I think you will find that, yeah, seen that. Appendix. Yeah. Image and text retrieval. Then you can see in table 13. Yeah. See, this is text retrieval, and this is image retrieval. And these are I wouldn't call them a supervised based method, but you can definitely you can see that these are some methods with the pre-trained models. Yeah, and you can see that. Of course, nowadays the sorted model are the fine-tuned models, or the models that are supervisedly trained. But you can definitely see that the zero-shot clip is the best among all the zero-shot based methods on different configurations and the task data sets. Very significant improvement. And I would say for certain subtasks, it's better than the fine-tune model, which is very surprising to me. And for the data set that's not as good as the fine-tune based method, but it's very close. It's very promising, I would say. Very promising. You see this? It's very promising. I mean, this is a very, I would say this is a very good result considering they are just doing zero-shot transfer learning. Okay. Back to section 7. Page 20. Yeah, we finished this. And OCR results. I think I would jump over OCR. You can see that the OCR thing are roughly similar to their image retrieval search. They do better than other zero-shot based method, but it's still behind the sorter based method. And the take-home message is that many of the clips capabilities are omni use in nature. I don't know how you understand this sentence. Okay. I think after they talk about the basics, they move on to the most important part in this section, bias. Bias section, I think the results are interesting to me. First of all, you check the table number 3. It shows the fair face is a data set which was designed or collected to tell whether the model can fairly recognize the race, gender, or age of a human from his or her face. These are the baseline model, okay, fair face model baseline. But if you have the clip model, you just add a linear classifier on top of it, and this is supervisedly trained. Okay, this is supervisedly trained because you have the fair face label, right? You can train that supervisedly, and the zero shot means it's a supervised learning. And what is the linear probe Instagram? It's probably trained on Instagram. Another pre-trained model. It's not a clip. No, this is not a clip. This is for comparison purpose. So you can see these two are comparable. Make sense? And these two are comparable. Make sense? These two algorithms are comparable. And you can see that zero shot when regarding the race, so you can see that suppose you have a white people's face. The zero shot clip wasn't doing very well in classification, but once you supervisedly train it, the result became very good, almost as good as fair face model. Remember, this is just using a linear classifier. I suggest that if you use the more sophisticated class, the result might be better than the fair face model. And also, it's interesting that the gender and age is the best of all the 4 algorithms they compared, which means the clip model is fairly unbiased when recognizing the category white people. And then for the table 4, they're showing the percent accuracy on race, gender, and age classification of the fair face category, non-white. And I think the general conclusion was the same, except that this time the zero shot clip works way better on non-whites than on whites. See this too? That's what I perceived. Makes sense? And when you break down the results of table 4, I think, then especially on the gender part, you check the subcategories, because you can see they show the Black, Indian, East Asian, etc., and they put it over here. This shows to you what's the individual result of subcategories looks like when it goes to male and female. But there's too many results. I tend not to go into it. But if you're interested, you can look into it by yourself. Because, yeah, the 98, 97, I think would rather to use the errors other than accuracy. So that would be more clear to people who check the table. And let's see table 6. This is more interesting. They're saying that suppose you show a arbitrary image to the model, okay? Yeah, still clip model. So this time it's just a clip model itself, and you will see that this is a misclassifications or wrong classifications or wrongly classified. So you can see for crime related categories, the white category is the most wrongly classified, or the categories that is most likely to be misclassified. And also Indian is the second, and Black is the third. So when it comes to the non-human category, I think, no, not I think, the result shows that the Black category is the category that is most likely to be wrongly classified. Now, who's the second? India. Again, white is the third. It seems that the model does not make, or is very unlikely to make a decision error on the East Asians. And I would, especially the crime-related categories, I would rather regard that as also maybe as a bias. It tends not to give crime labels to East Asian, and also they even never give non-human label to East Asian. that's also a bias, in my personal. Okay. Table 7 or table regarding table 5. I think that oh yeah and they also track the ages, okay, of the classification, but also still the crime related and the non-human categories. So this is the results, using the default label set. Remember, and when you do the zero shot inference or learning, there is a concept list, or what they talk about is the concept list is the label set here. The label set could be whatever label set, okay. But you can see the errors or the misclassification rate is fairly high, especially for the people who aged from 0 to 20. I didn't get that. How do they label a 2-year-old or 5-year-old as criminal? That's something that is not very understandable to me. But once they add another category, which is child category, you can see the results or the misclassification significantly dropped significantly. And after this, you can see previously the highest misclassification category is 3 to 9, but after this it became 50 to 59. So this is what they suggest by the authors, that this is the importance of the class design, because it can have the potential to be a key factor determine both the model performance and the unwanted bias. Okay. So this is how the human knowledge or human kicks in for the zero shot transfer learning. Remember that section 2 also talks about the voice prompt design. So if you design the voice prompt well, it can boost your classification accuracy. Well, the same thing happened here. If you can just design your classes or the categories in a proper way, and then you can probably or very likely to remove the unwanted biases. Yeah, this is a take-home message. Poor class design can lead to poor real-world performance. Then they carried the following 3 experiments because they wanna check the this is also interesting. They want to check the accuracy on gender classification, and they test for how labels were differentially distributed across 2 different label sets. So for the first label set, they use a label set of 300 occupations. So what the occupation could be, for example, congressman, doctor, director, things like this, or occupations. And for the second label set, they use a combined set of labels that coming from the APIs. The APIs including Google, Amazon, Microsoft. So you may ask, what are these labels? I think if you just call the API documents of these companies, they will tell you how many categories or the categories of the images or the labels of the images the API may return. They just have a union operation on these data set, these labels. Okay. I just wonder how many labels they got, but I don't think they say that this. But it's way more than 300. Should be way more than. Yeah, they come up with first come up with the common sense. So when the data set, a member congress data set were high quality or unclear, they found the model got 100% accuracy on images. Remember, this is gender classification. Okay. I think it's difficult to run gender classification on member congress images because they are so clear, high quality. And then they do this. They set thresholds for label probability. And so they did an experiment in which they set a threshold value at 0.5 and 4.0. Here's my understanding of their text. Okay, suppose you have the axis is the label categories or labels. How do you say that? Let me just say labels. Okay, the label can be car, dog, congressman, doctor, things like this. And after you do the zero-shot learning, you will find, okay, I would have these probabilities, right? Drawing is awful. The cat. A car, sorry, car. So this is probably a car, probably a dog, probably a congressman, and etc. And they would only regard the results as valid if the maximum probability exceed a certain threshold. So this is a threshold. So the threshold can be either 0.5% or 4.0%. You may ask why the probability is so small. It's because there are so many categories. So this is why you may get very low probabilities. So then the conclusion they got first is the lower the threshold is, that leads to the lower quality of the labels. Well, you can regard the threshold as something like a confidence score of your recognition results. Remember, in the speech recognition, the system can refuse or suggesting that the recognition results might not be reliable if the highest probability of the candidate falls below the preset threshold. Okay, that means the distribution of the candidates is kind of flat. Okay, they don't know, or the system doesn't know which one to pick. The same thing here. So they're saying that if the interesting example is that if they set the threshold to be 0.5%, which is a lower threshold compared to 4.0, and then the strange thing happened is that, or the unwanted bias happened. The nanny housekeeper started to appear for the women image labeling. So suppose you give system a image of woman, and you set the threshold of these labels to be very low, like 0.5%. The system tends to, biasly label the image as nanny or housekeeper. And also for men, they tend to label them as prisoner and mobster. And when you set the threshold to be higher, like 4.0, things are more making sense, or less bias you would be preserving. And you would see that, okay, let's just scroll down a little bit. So this are some images, labels you see the model would label people, okay? For instance, these are showing the top labels of image of women, besides women. There, I didn't quite get why there are two colors. The top 20% most gender labels for men and women were identified with chi-squared threshold 0.5%. Bars denote the percentage image for a certain label by gender. I'm sorry, I'm a little bit short circuit here, but I'm coming back to here. They're suggesting that at a higher 4% threshold, the labels with the highest probability across both gender include lawmaker, legislator, and congressman. Yeah, those are the labels. But it says that although you can see, okay, I can raise the threshold to make the unwanted bias to be less. But the question is that even if you set a high threshold, can you say, okay, I safely removed, or this is sufficient to remove all the unwanted bias, or something like called safe behavior? That's something, the paper didn't answer. Something needs to be explored. I would rather take this picture for figure 18 as some interesting thing to take a look at. I don't think the authors run into any deeper analysis of this, but you may say this is interesting. When you got a man, you can tend to give a label of suit and a tie or necktie. But when a female image or women got shown to the system, you can get labels like blonde, hot, hair, and things like this. These, according to the authors, they regard them as signs of bias. And they're saying that, interestingly, when you set a higher threshold, let's say 4% threshold, they're saying that many occupations oriented towards like a military person or executive, when you set a lower threshold, So when you set the lower threshold, those labels, when they're used to label men images, can be shown in the labeling of women images. But the reverse was not true. So even you lower the threshold, which means more bias would happen, but it's unlikely to to bias against the men, because this is what it's saying, that description words used to describe women were still uncommon among men. So it's unlikely to, I wouldn't say called bias, probably not bias. The word, for example, blonde, even you set the threshold low, the bias start to appear. For example, the blonde word may still not be appear on man images. Clear? But things like a military person might appear on women images. Yeah, here is something you want to take home. Decisions about things like class design are a key determiner, not only for model performance, but also of how and in what context model bias manifests. Okay, then we move on to the subsection surveillance. Because surveillance, I think, according to the authors, there is a significant societal sensitivity. There are some references, because they're saying that this is an important domain, whether the system could make predictions about given its societal implications. And they have two data sets, I think, on two data sets. They first test the model on low res image captured from CCTV, low res CCTV, and they also use the Virat data set. Oh, this is the second data set, and also the third data set. Oh, these are two data sets, but they're regarded as just one data set because it contains both. It both contains real world outdoor scenes. They both contain the real world outdoor scenes with non-actors, but I think this one contains a lot of celebrity images of CCTV. Correct me if I were wrong. And then they perform the coarse classification and the fine grain classification. Coarse classification just demand the model to do scene classification. For example, parking lot, school campus. But the fine grain classification, they want the system to identify the presence or of a smaller objects or features in the image. For example, a person, cat, or dog. This is more like a classification. This is more like identification. Okay. The regarding the results, where is the result? Kind of I think they put in a remember I saw that. Let me quickly go to the appendix. Sorry, no, not in the appendix, or maybe I missed it. But just let me look at the numbers, okay? They're saying that the model had a top one accuracy of almost 92% on CCTV. This is the first data set, okay? This is the second. This is the first data set. And then the accuracy dropped significantly for the second evaluation. So they're saying that for the celebrity, they're doing better. But for the non-actors, the real world scenario, this works very bad. It's even around 50% accuracy, and the model would incorrectly choose the close answer 40% of the time. That means it likes to confuse one thing for another one. This is the coarse classification. And then for the fine grain detection, the zero shot performed the poorly. Yeah, it's so sad to see that, but it makes sense. It nearly like random guessing, right? And then they also check the clip model zero shot performance for the in the wild. I think this is called a WIT, right? Not WIT. In the wild identity detection using the celebrity A data set. Or I think what's very yeah, you just see the take home message is that it checked the table 8. So they're saying that when the number of celebrities in a classes, sorry, when they're limited the amount of celebrities appeared in the data set, the performance was not very good already. It's less than 60%, But when they increased the amount of celebrities in the testing, it became worse and worse. So I think they also commented that for surveillance, this might not be usable compared to the supervised based model. Okay, because if you check the supervised model, they're saying that large datasets and high performing supervised model exist for many in-demand surveillance tasks. So this is means clip may not fit for this because the accuracy is not there yet. But it does unlock a certain aspect of usability because it doesn't need or doesn't require the existence of training data. Yeah, just look at that result. It's understandable. You say, suppose because they train on the internet data, the data might have seen already the celebrities, so they can go fairly well on the the scene classification. They don't have to label scenes because the data they got from the internet are fairly mostly coming from different type of scenes, right? It has different concepts attached with the internet image. So they train the model well, and they can use the model for the zero-shot classification, for the sync classification. But once it comes to the identification or detection, the system doesn't work very well. Yeah, these are suggesting that that's a future work. They listed several potential future works, or the future directions, or the future things, or the future research work may be benefit from the clip model. One thing is the downstreaming use. I think this is common sense. And also, this is something beyond my understanding. Some policymakers may use this. And this is also something that I have to understand better. They say they can be used to characterizing the bias in them. But from the analysis, I think what it meant is that you carefully design your categories to avoid or eliminate the unwanted biases. Okay, then yeah, I think that's great suites. Yeah, identification is failure. Okay. Yeah, I think they're also saying that they plan to contribute to these things. So let's just keep tuned. And the last section, and they talk about the related work. I can't go over this, but I don't think I can go over it today because it requires me to read lots of NLP and the computer vision papers. But as you know, I'm mostly like a speech and NLP guys, or most of speech guys. But most of the papers are not very familiar to me. But if you're a computer vision guy, you definitely have read all of these papers, because all the papers they mentioned about here are mostly classical papers or highly cited works. I do recommend you to read all of them if you're fairly interested in the clip. The conclusion. I think their conclusion is fairly straightforward. First of all, they're emphasizing the clip model was originated from the attempt to transfer the success of NLP work. Because in NLP, you look at the BERT. BERT is capable of doing zero-shot learning, and that's task agnostic, and BERT uses lots of web text, web data, and they adopted this formula to the computer vision domain. Remember, this task agnostic web scale. They got some zero-shot learning working here, and working fairly, I would say, fairly good. And they also use the web data. Remember, they have the image and the description or text pair they grab from the web, over 400 million pairs. So this is they made it successful working. And they also talk about the social implications, and they're saying that because they do zero-shot learning, they can be used for a wide variety of tasks. Okay, it's just like BERT. Okay, BERT can be used for almost any NLP-based task. And they're saying that the zero-shot based learning, the performance is not as good as these supervised sort of model, but that the performance are definitely comparable for certain data sets. And I personally agree with them. the zero-shot based methods are fairly, especially the zero-shot clip, are fairly promising in the future. Or they're, in their word, competitive. So it's not done yet. Let me quickly go over certain experiment we talk about in the experimental section or appendix section. This is the take-home message. Remember, Vision Transformer is much better in the clip setting compared to ResNet. So when you play with the clip, you should definitely play with this Vision Transformer as your encoder or image encoder. Also, I think I will skip this. This is about datasets settings. These are the breakdown numbers of different models they compared with. These are some different datasets. They have the, what do you call that? Yeah, different. This is a linear performance for different subsets. And these are some examples or visualizations. I will skip them. This one I think is trivial. Zero performance compared to linear performance. Yeah. There's lots of comparison. Comes to the duplicator detector, we have covered that. And they have done the dataset ablation on YFCC 100 million. Why they did that? Because think about this. They trained some, the model was trained on WIT. I think W means wild image and text. That's my guess, okay? But that's roughly what they meant. Correct me if I'm wrong. My memory says this. They grab all the data from net, but you can also just use some pre-existing data set they call the YFCC 100 million. Definitely the WIT is way larger than YFCC 100 million. They talk about that eventually. They're saying that the YFCC is only less than 4% of the overall WIT. Less than 4%. So WIT is way bigger than YFCC 100 million. But they want to see that whether changing the content of the data would affect the performance of their clip model. So they limited the training data size or to be smaller. So this is only, so this WIT is not a full WIT. I think it's just a 4% of the overall WIT data set. So the two data sets has the same size or roughly the same size. And the conclusion was that first check the average. You will see that for the linear classifier and the zero shot, the performance doesn't change much on average. Of course, for different sub-data sets, sometimes the YFCC are better. YFCC is better, but sometimes the WIT is better. See that? Win and loss, okay. But it seems that to me, WIT data has better quality, or it's more efficient than YFCC data for the clip model training, because you can see finally the dataset average, they get better results for on a linear classifier and also the zero shot transfer learning. And although this one they lost the one, but this one is a big win over the YFCC data. Okay, And this suggests that, of course, it's a winning, but I think the author wants to say that as long as you have lots of data, it doesn't matter much how you organize the data. Make sense? So the quantity is more important than the quality, or quantity is more important. What else? I think I covered this image and the text retrieval, and the OCR recognition. OCR. Is it OCR? Yeah, you said OCR is the same. Let me just say quickly go over the OCR. You can see that it's behind the sorta, but it's fairly comparable or promising. And think about this. Suppose they're doing the supervised learning. ES best means all the best model you can find from the papers. The clip model beats all of them. That means that the base or the clip is fairly strong. But definitely, even you beat them, these are still behind the fine-tuned model. You see this? Still behind, right? Not there yet. Might be need some more fine-tune. That's something I do not know, because, or you can just change the linear layer into some more nonlinear classifier that should be doing better. Whether that's going to be better than the Solar is a question. But I think the author, their focus is not the linear classifier. This is their focus, zero-shot clip. That's their main focus. They want to demonstrate their model can be generic, can be something like AGI. Yeah, AGI, general artificial intelligence things. If that's zero shot. They also talk about action recognition in video. This is a good question, because they are saying that most of the labels in the ImageNet are nouns, or proper nouns, verbs and adjective. Okay, and the ImageNet 1K only labels common nouns. Okay, but the clip model is basically trained with visual concepts. What are the visual concepts? For example, something like eat the pie is a visual concept. Correct me if I'm wrong. So it's different than just the simple words. Am I right or wrong? But it seems that the point is that, might be wrong. I think the point is that the clip is trained with a wider range of visual concepts, but the ImageNet is only trained with the common nouns. Okay, makes sense? They want to say that, okay, when the task is action related, so there's no common noun involved. Okay, how the model would work. Of course, the model is still behind the fine-tune model when the clip is being used in both linear and zero shot scenario. But you can see in the in the linear case, linear supervised model, linear classifier supervised model, clips works better than the other best methods. And for the zero shot cases, especially the rare act, compared to another zero shot based method, a clip is way better than it. And I guess this one, according to the author, they use it's a fully supervised baseline, which is trained on this amount of labeled videos. Makes sense? I think that they're saying that because it because they have a strong performance on the task of action recognition. The authors they talk about the difference compared to the so the difference might be not just the form of supervision, such as model architecture, things like this, but also, it needs, this is an important take-home message, is more precisely determine what specific design decision contribute to achieving high performance on this task. Design decisions. Okay. And they also compare the geolocalization. Yeah, I think I would skip this because I have to say that I forgot to read this image, but I think the result is consistent with the previous conclusions. Geolocalization, I think it's here. So you can see it's still not as good as the state of art, but it's very promising. It's getting there. The robustness to distribution shift. Oh, that's table 16. Let me quickly see if I can understand it. Yeah, so this is the ImageNet, or the original ImageNet, and these are the variations of the ImageNet. All these are variations, so that you can regard this as distribution shifted ImageNet. Make sense? ImageNet. So they want to see how the clip model works when the distribution has been shifted. And then you can see that the model worked on beat the other sorter model. Actually became the sorter model when the distribution shift is big. But I guess for these two, the shift are not that big, so you can see the difference is actually huge compared to sorter model. But this is my question. I think this is probably unfair. Oh, I see. This is a fair comparison because when the model for example, the NS efficient net L2, the model was trained under ImageNet, but when they test on ImageNet R, they're not doing fine tune on it. They're still doing something like a zero shot on this model. They're using the original model trained from ImageNet because they have a distribution shift. They have something we call the mismatch, and the performance dropped significantly. So this is a real world scenario of zero shot, and they failed in many cases. You can see sometimes you would see the difference between the a zero-shot clip versus the best model is big. The difference is big. But I think this is the advantage of the zero-shot clip, as the mentioned. They can handle the distribution shift. Remember this distribution shift. Okay. This one, yeah, the robustness to zero distribution shift. This is the table 16 people just covered. And I think this paper, Tori et al., I think to me is very interesting because for speech recognition people, we're handling with the distribution shift all the time because the accent, room acoustic, and the speaking style, these type of things. Even one person is speaking, the same person was speaking. The speech of is the dictation and the spontaneous speech would be a dictation, and the read speech would be different, would have a different distribution. So I would just, for myself, I would definitely spend some time read this paper and see how Tori and his colleagues evaluate the distribution issues of ImageNet. This is an important, interesting paper to me. Okay. Model hyperparameters. I think these are some parameters if you're really interested in playing with these experiments mentioned in this paper, you should look into this. Right. Finally, okay, we finally finished this 48 pages clip paper by OpenAI in 3 parts. And this is a last part, part 3. So for those of you who have not seen the part 1 and 2, and if you're interested in the clip work, I highly recommend you search clip in the Olewave channel and watch my detailed illustration on the introduction, approaches, experiments sections of this paper. All right. If you like this video, please share that with your friend and subscribe our channel. Goodbye.